Okay, so yeah, let's continue to talk about um uh some lecture material. So uh yeah, also let me just give a quick recap uh from the content up to this point. So from week 1 to week 5, what we have introduced is two branches of random uh, two branches of ways to describe some random phenomena. So we have seen one branches is called a discrete random variable. So we can, if our intention is to measure, for example, like out of the 10 coin flips, how many of them are landing on a head, then that fall into the regime of using discrete number to represent that kind of random phenomenon. And then we can use a discrete random variable to measure or to quantifying those kind of random behavior. We also have the case where things are continuous. For example, like the duration, for example, like a continuous time or some measurements, you can take the value of 5.1 and also 5.12. So in that kind of regime, we can use a continuous random variable to quantify or to measure those kind of random phenomena. And then we also talk about some of the underlying formulations to describe the random behavior. So for the discrete case, we have the probability mass function. Okay, so that will be functions to describe to describe the random phenomena of that random variables. And then for the continuous case, we also have the probability density function. And then we also give examples regarding, so in the discrete case, we can have the binomial distribution. We can also have the Poisson distribution, that we can use these distributions to measure like discrete count, like how many heads we get on 10 coin flips. And then for the continuous case, we have also introduced the exponential distribution, the gamma distribution, and also the normal distribution. Okay. Okay. And then we also talk about the corresponding moment generating function. So for this part is the functions that you can describe the random variable. And then for both of them, they all have the moment generating function. Okay, so you will also have the moment generating function for discrete case and also the moment generating function for the continuous case. And then we introduce through the moment function, we are able to calculating the moments, which is the expectation of x raised to the power of k. And these are all shared or statistical concepts that are shared no matter you are in the discrete case or the continuous case. So they are statistical concepts that will fall under both regimes here. Okay, so that is a quick recap of what we have done in week 1 and week 5. And now, under once we have those kind of like some prerequisite, now we are able to, after week 6, now we are able to talk about the probabilities based on these random phenomena. So these are so what we have to talk about from week 1 to week 5 is like a prerequisite that we introduce some of the tools that are ready for us to talk about the probability. So now we are going to talk about the probability, and then it can also be discussed separately through the discrete case and the continuous case. And last week we have seen many examples in calculating probability for some random events or some experiments that we cannot predict some outcome with certainties in the discrete case. And today we will gradually moving toward the continuous case. Okay, so I would also just like to give a quick recap for the probability in the discrete case, and then we will see from there how we can gradually move to the continuous case. So now we're talking about we are ready to talk about probabilities from the tools that we provided in week 1 and week 5. Okay, so when we talk about probability and also for the discrete case, we started from the binomial distribution. And then our motivating example is that we are flipping 3 coins. Okay, and then we have created a table where we have 3 head, 3 tail, and then we also have the case for 2 head. So these are just the notes from your from last week. So feel free to not you don't need to write down what I'm writing, and because you already have these notes. Okay, so we will have this kind of tables. Okay, and then based on these observations, we have invented the binomial density function in the way that this is the probability, the PMF that we introduced previously. And then we have invented from scratch on calculating the probability for each of the outcome from the table. So just as a recap, we have n coins. So in this case, it's 3 coins. And then we want to measure the outcomes, which is we cannot predict with certainties. So it's a random phenomenon. And then we are interested in k of them are landing on head. And then so the binomial coefficient here will handle the counting parts, where you can have the 2 heads, but they can locate it at different location, like the first coin or the second coin or the first coin or the third coin, that kind of random behaviors. And then we also have the probability for each of the coin landing on head, and then we need to raise to the corresponding, the one that we observe k times of the head. So we have the p is the probability of landing on head for 1 time. And then we also have to account for the k times that we observe all of the n coin flips. And then that means we also have the n minus k times for landing on tail, and the probability of landing on tail is 1 minus p. So we essentially just invented the binomial density function, the density, the mass function. So we just essentially reinvented this probability mass function. Okay. So that's what we started with. Through a coin flip examples, that particular random phenomenon, we can use this mass function to describe the random behavior of how many heads landing on out of n coin flips. And then we mentioned that for the discrete case, let me here for discrete random variable. Now, if we want the probability of this, the probability of, let's say, the random variable, how we measure or how we quantify this outcome from this random behavior, let's say the probability that the x getting on k head is just the outcome from the probability mass function. Okay, so you can see that the probability mass function is just the tool or the mathematical construct to give you the probability, and if this is your interest. Okay, so just the outcome from probability mass function, when you evaluating, when you plug in the k into this probability mass function, then it will directly return you the probability for the things that you are interested. Okay, so the mass function is a tool or a formula or a function that will when you input the k of your, let's say if we're interested in k equal to 2 out of the 3 coin flip, when you input the 2, the 2 that you wanted to calculate as corresponding probability, then the outcome of that probability mass function will just be directly, or the probability for describing the probability that you get 2 or k hats out of n coin flips. Okay, so the probability mass function give you the ability to calculate the probability directly. Okay, let me pause here and see if there's any question or comments up to this point. Okay, now let me just provide a quick example, which is also the same from the previous lecture notes as a quick recaps. And also I want to show kind of like a migration from this discrete case when we can invent the binomial coefficient from scratch, move to Poisson, and then by the end of the lecture, I will talk about exponential, what are some questions that will need to use continuous probability density function to calculate the probability. And then to calculate the probability, we no longer have this kind of behavior that the output from the probability density function, we will need to do some other things to get the probability for continuous case. But the probability density function is the foundation, is the function that will be the tools that providing us the ability to calculate the probability in that case. Okay, so the example that we previously also talked about is that there are, let's say, there are 10,000 trials. So this is the n in the binomial density mass function. Okay, so we will have 10,000 trials with the probability for each 0.003. Okay, so this is the p for the binomial NP. So in this general context, you can consider the n here is like we have n coins, and then each of the coins have the probability of landing on head 0.003. Okay, so this is the coin, and then this is the prob of landing on head. But here we just, instead of using the general, instead of the coin flip, we just use a general context that the trials and then the probabilities for success. Okay, so instead of the coin flip, so you can also regard this as we have 10,000 coin flip coins, and then each of the coins landing on head with a probability 0.0003, and then that means we are able to use the binomial distribution to measure or to evaluating some of the statistical quantities, for example, like probability for this particular context. Okay, so in this case, now let's say we are interested in the probability of x equal to 2. That means we can directly using the probability, the binomial mass function to calculate the probability. Applying the formula, we have 10,000 coins. We are interested in 2 of them are landing on head, or two of the trials are success. Okay, so we have this to take care of the locations like the coin flip, the locations where we can have the first coin or the first trial is success, or the 1,000 trials success, and the other one are all failure or landing on tails. Okay, so we have this binomial coefficient to take care of that, the randomness at different locations. We just need 2 of them are success, or 2 of them out of the 10,000 are landing on head. Okay, and now to take care the probability that two of them are landing on head, we have the 0.003 raised to the power of 2. And then we also have the rest of them, they are all failure. So we have 10,000 minus 2 occurrence for the probability that is that they fail or landing on tail, which is 1 minus the probability for landing on head. Okay, and then we will have this. So one thing that we mentioned here is that back in days, there's no computer. So calculating this and also calculating these small value, but for a large amount of time is extremely difficult, or you will run into the issue that this will be a very small number and then it will get very close to zero. But in practice, or you will know that this is not a number equal to zero, just a very small number, but it will causing trouble to performing the computation. So then we have the case. So let me first providing this will be 0.224053. Yeah, but then when back in days people are not able to calculating this, then people come up with an approximation, so which is the Poisson distribution. Okay, so here to draw the connection with the Poisson is that we are going to using the moments, okay, which is the E of the X. So in week 1 and week 5, we have calculating that, or we have calculate that for, so for binomial, E of X is n multiplying by P. Okay, so out of the 10,000 trials, each of them has a probability of 0.0003, then you will have the expected, the first moment or the expectation is equal to 3. And then we also calculated the moments for the Poisson case, which is just equal to lambda. So you can either get these through moment generating function and also through the definition of the expectation. Yeah, but the key to make the connection from the Poisson to binomial is through this moments. So when binomial distribution is difficult to calculate computationally, people can use the Poisson distribution. And their connection is that we are letting their moment to be their expected value to be the expected value. So we want to use the Poisson density function, a mass function, to calculating the things that we are unable to do in the binomial. So to draw the connection, people use the first moment or the expectation to bridge between the two. So here we are using the moments, and essentially in this context, we are setting the lambda for the Poisson to be equal to the expectation from the binomial. And then in this case, in this context, we will have the 10,000 trial with the probability 0.003 that is equal to 3 when you for n multiplied by p, and then you plug in this expectation in the Poisson distribution, and we are ready to use Poisson distribution to facilitate the calculation where binomial distribution is difficult to evaluate. Okay, so now we will have for the coin flip two success out of 10,000 trials. Now using the Poisson distribution, we will have E raised to the power of negative lambda. So we will need to use the probability mass function for the Poisson distribution to calculate this. And then you will have the following. So these are just plug in the value. You will have 0.2240418. Okay. So you can see that the two value here are actually relatively close to each other. So just a quick as a history or a background is that when these are very difficult to calculate, you can always borrowing some other let's say statistical functions that are intuitive or realistically to approximate the value, and then you can see that they are very close. And the bridge that you can the reason or the underlying foundation that you can make this connection is through the moments here. So when we have when we are able to use the momentary function, the definition of the expectation to calculating the moments, and then that give us the connection. When one is difficult to use, we can borrow the other case or the other density or mass function to approximate the things. Okay. So the high level message here is that we can use the probability mass function to calculate the probability, and then we can use the moments to make the connection between different probability mass function to navigate. If some of them are difficult to work with, we can through the moments we are able to using other tools that are to facilitate the computation. Okay, so any question up to this point? And also last time we have seen that when, also this is from last time, when n goes to infinity, the binomial will also become a Poisson. So we have also showed this mathematically that they are in the back end or under some configurations, they are essentially the same thing. And then you can, if one is difficult to evaluate, you can always use the other one. This is also the similar idea when we're talking about the moment generating function. If the definition of the expectation or the moments are difficult to calculate, you can first calculate in the moment generating function and then calculating the moments. So here are all just different tools to answering the question of your interest. So if this is your question of your interest, the probability out of 10,000 trials, if that is your questions, and then you want to answer that, you can have these two approaches to calculating them. So if binomial is difficult, you can use Poisson and vice versa. And the connection is through the probability mass function, and their connection is by we bridging them together by the moments here. So now when we're talking about the probabilities, we can see that the things that we introduce in week 1 or week 5 are the foundation or the are the core that facilitate our discussion when we talking about probabilities. Any question or comments up to this point? Okay, so now let's also talk about another examples. So here, a call center receive an average of 2 calls per minute. So now let this discrete random variable x be equal to the number of calls in 1 minute. So let's say we are interested in the probability of x equal to 3. So that is saying we are interested to calculating the probability in this call center that we will receive 3 calls in 1 minute. Okay, so now when we're looking at this questions, we can see that we are provided by an average of two calls. So we also know that this is a discrete case. A discrete random variable. So now we have, so far we only talk about binomial and Poisson, and then when we are giving an average, a specific counts. So like two calls per minute, then one direct way, or when for calculating probabilities, we can, one way is that we can use the Poisson distribution to measure that when we are giving a average call equal to 2. So that is saying, if we choose to use the Poisson, then we can work with the Poisson density function with the average equal to 2, which is just setting the lambda equal to 2. And also, as the side notes, the expectation of the average number is equal to lambda. So when we look given a question that we have a count as an average in the 1 minute, in the, let's say, two call per minute, then we can use Poisson, and then by letting the lambda, the parameter of this Poisson probability mass function, the lambda equal to the average number that is given in the question here. Okay, so now to calculate the probability, and we choose to use Poisson, and let's say we are interested in 3 calls in the next minutes, but the average number per minute that this call center will receive is 2 calls. So let's see what is the probability that we'll get 3 when the average is about 2. Okay, and when we choose the Poisson, we just use, and we also know that the probability is just the outcome from the probability mass function. So here we bring in the probability mass function. So we will have e raised to the power of negative lambda. In this context, the lambda is 2, negative 2. We will also I think it's e raised to the power of yeah. So the probability mass function is e raised to the power of lambda, so negative lambda, so negative 2. Yeah. And then we will have the x raised to the power of k. Let me revisit the probability. Now, lambda raised to the power of the k. So we will have the lambda is 2 raised to the power of the number that we want to observe. So in this case, is 2 raised to the power of 3. And then we have the k factorial, which is 3 factorial. And then let's see, if you evaluating, so let me evaluate this at the using calculator. Give me 1 second. So exponential negative 2 and 2 raised to the power of 3 divided by 6. This is about 0.1 18047. Okay, so this is what I get from, so this is when I think, so this is when I plug in the number to the probability mass function that I get. Okay. Okay, so when we are given this type of question, when we are given an average call per minute, and then we are interested in getting 3 calls, when we know that the average is about 2, and we choose the Poisson, then this is how we can set up the question. Okay. Last time we also showed that we can also use binomial, or last time we showed that we can use Poisson to approximate the binomial. So here, let's do it in the opposite way, just to give you a sense that we can always choose a different way to, so as long as you think it is realistic, you can always choose different option to calculating the probability. So there's no right or wrong. It's just based on the tools that you have, and then you can choose based on your setting or your assumption or that kind of intuitions, and then you can use all these tools to calculating the same thing. So now let's take a look at how to use a binomial. if you believe that the binomial is also realistic, and let's see how we can use the binomial probability mass function to calculating that. Okay, so now we have the same problems, and now let's consider in a binomial density distribution a way of thinking. Okay, so if you still recall from last week, when we use Poisson to approximate binomial, is that when we have 1 minute and then we break it into 60 time or 60 seconds, and then out of those 60 seconds, we can consider each second has a trial or has a coin flip, whether it's success or not. And then we will have 60 coin flips, and then let's say here 3 of them we are having a landing on head, and then the remaining 57s are landing on tail. So that is how we convert a binomial distribution into a Poisson way of thinking the same problem. So now let's do it in the opposite way. So, and also the idea here is to give you a sense that you can always use different way to solve the problem as long as you think it is realistic and also it aligns with your underlying assumptions. Okay. So now let's use binomial to kind of approximating the Poisson, assuming that we are able to calculating instead of like when things are very large, like n and p are large and small, then we are not able to calculating that. Okay, so now let's do it in the opposite way. So here we have about 2 calls per minute. So let's use the way that the approach to dissect this kind of problem from last time. So we can also consider this 1 minute as a sequence. Let's break them into 60 time slot, and then maybe one of them are 1, and the remainings are not success. And then in this case, in this 60 time slot or this time horizon, we are also just using a binomial way to dissect that based on this information given to us. On average, 2 calls per minute. So in option 1, we're using Poisson way of thinking the problem. When we're giving an average, we know that the moments, so this is the expectation. That's the Poisson way of thinking. Now let's think about the same problem by using other options that we have. So we have the binomial way, and then we have 60 seconds. 2 of them are, let's say, landing on head, or we receive a call. The remaining seconds, I think we need 3 of them. Okay, so maybe we need 1 more. So we are interested in 3 of them. So our problem is that we want 3 of them, 3 calls. So that means on average, this call center, we will receive 2 ones in this 60 time slot. We are interested in observing 3 of them and calculating the probability. Again, the probability for discrete random variable is the outcome from the probability mass function. So now this is saying we have a binomial. So if we choose to use the binomial way to thinking about this problem, this is saying we have n equal to 60 coin flips. We know that the probability for each of them, if you thinking about the binomial case, that is saying we should have 2 out of 60 times slot are success. So the probability for each of the coin flip landing on head or receiving a call out of the 60 time slot is 2/60, because we are given that we should getting on average 2 calls per minute. So that is saying the probability of, let's say, out of 60 coin flip, 2 of them are landing on head. So the probability of each of the coins landing on head is 2 out of the 60. So that will give us a probability in a coin, so prob of head for 1 coin way to thinking about this problem. Okay, so this is the binomial way to thinking about the same problem. Okay, now we choose on the binomial. Again, the probability of a discrete case is just the output from the density mass function. So we are interested in x equal to 3 for that probability. Now, borrowing, so instead of Poisson, let's use binomial. So we have 60 coin flips. We want 3 of them landing on head. For 60 seconds, we want 3 of them are receiving a call. Each of them will have a probability landing on head or receiving a call of 2 over 60. We want 3 of them. 1 minus 2 over 60 is the probability landing on tail or not receiving a call. And then we want, in that 60 time slot, we want 60 minus 3 of them. Okay, and now let's see if we consider the same problem in a binomial way, what is that probability? So let me do this on a calculator. Okay, give me 1 second. 2 over 60 raised to the power of 3 and 1 minus that. We want 57 times. Okay, so we have 0 0.183523. Okay, so now, so this is just a one example that we are now given a kind of like a real problems, and then we are interested in the probability that x equal to 3. So in this context, it's like 3 calls in 1 minute. Or if you use the binomial way to think about this, it's like 3 landing on head out of 60 coin flips. So this is kind of like a showing you that using the now we have the real problems and how we can use the probability mass function that we introduced before to facilitate when we are interested in the probability of these random behavior. And now the probability mass function here are the tools for you to calculating the corresponding probability. Okay, so let me pause here and see if there's any question or comments. And also, are you guys still there? Okay, yeah, you guys are still here. Okay, yes, great. Yeah. Any question, comments, or thoughts? Yeah. So you can see that when you guys are familiar with the probability mass function, and now when we move to the probability, it's just like a one step ahead, one step extra thing to calculate, and then it will have some other intuitions here and there, but that you already have all the tools that you need. You just want one extra step to calculate the probability. Yeah. Any question?
Is one of them like more correct, or do we just choose what to
There's
use?
no, yeah, that's a very good question. There's no correct or good way. It just depending on how you consider. If you believe the Poisson is more aligning to your way of thinking or the binomial way, you can choose either of them. They are both correct way to or intuitive way to calculating the a probability of something of some random events. Yeah. So for example, when we are giving a real problems, you can choose either Poisson or binomial, and then they just give you some under the binomial way, what is the probability that these things will happen, and the other ones give you under the Poisson distribution, what is the probability that this is going to happen. Yeah. But there's no right or wrong or more correct. Yeah.
I think Matson had a question in the chat.
Oh, sorry, I'm not able to see it. So can you, if yeah, I can only see my screen, so I'm not, uh,
I believe the question was regarding home if there's going to be homework 3 and if there's midterm 2 is happening next week.
can,
It's a little bit higher up.
uh, okay. I think there are quite a few. Sorry, I'm not able to see the text when I'm talking about uh, homework three. Okay, yeah, yeah. I'm going to assign a homework three today, and then there will be a midterm two next week. Yeah. Uh, oh, okay. Yeah, yeah. So, yeah. Thanks. Yeah. Sorry. I'm not able to see the text, but yeah, yeah. There will be for next week. Yeah. Yeah, and also for the homework three, I'm right now thinking about assigning so basically some kind of this type of question, and then I'm going to ask you to calculate the probability, let's say the Poisson way and the binomial way. And also, one thing is that I might ask you what is the sum of two discrete random variables. And the idea for to handling these are moment generating function and properties, like homework two. So those are the tools for you provided to you when, let's say, you have two call centers. If you think they are Poisson, each of them are Poisson, but with slightly different parameters, then you will need homogeneous function and properties to get the sum for x plus y. You need to get the density or the mass function for x plus y first, and then plug in the number corresponding to the mass function of the sum, and then performing the calculation. Yeah. Once you identify the discrete case, the new probability mass function for the sum, and then the rest is just plug in the number, the output from the new probability mass function will be the probability of that. Yeah. So yeah, right now this is one random variable, but if you need to do the sum or even the average, let's say 1 over 2 x plus y, then you will need to use the properties of homogeneous function to identify what is the new density, and then from there calculating the probability. Yeah. Okay, let me proceed, and now I'm going to talk about maybe okay. Now I want to talk about continuous case. Okay, so far we have calculating when we have quantifying or measuring things that are in discrete count. For example, like 3 coin flips out of 10 toss, and also two phone calls out of 1 minute. You can consider that as 60 coin flips and then two of like the previous examples. Okay, now there are also things that are not or cannot be measured in a discrete manner. It has to be like a continuous case, like okay, so um so we are talking about x that are taking in real values. So for example, let's say human height, we can have or a height of a tree, we can have like a 7 meters or 7.15 meter or a 9.52 meters. So there are lots of things that are in the nature that are no longer just discrete, they are continuous value. So then the idea or the underlying foundation here is to use the probability density function to describe these the randomness, the random phenomena. For example, when you walk in a forest, you're picking a tree and then you measure the height, and then the tree of the height of the trees will be at different values. And then to calculate the probability, you will need the probability density function, so the PDF for the continuous case. But different from the discrete case, the when we're talking about continuous random variable or continuous measurements, the probability that we are interested are the following. So we are interested in the probability that x is greater to something. So instead of that, in the discrete case, we're interested that the call, we will receive exactly 3. We are interested in the probability that the height of the trees are greater than a. So we need a range for that. And then for calculating the probability of this kind of events, let's say the height of a tree, what is the probability that when we walk in the forest, the height, or in this forest, the height of a tree is greater than a, let's say 10 meters. And then in order to calculating this probability in a discrete in a continuous regime, then to calculate the probability, we need to do the following steps, which is evaluating the integral from a to an arbitrary upper bound. So if there's no specific upper bound, then it will go to infinity. And then the density function, the PDF dx. Okay, so that is saying for the continuous case, when we talk about the probability, it's usually referring to the range. So in this case, the probability of that random that the height is greater than a particular value a, then when you want to calculate the probability, it's no longer just the output of the probability density function. It will be the integral from a to its upper bound. And if upper bound is not given, then it's the infinity. And then you plug in the probability density function here, evaluating this integral. Similarly, when we are interested in the probability that x is less than b, then you will also need to calculating the integral from an arbitrary lower bound. And then if lower bound is not given, then you will need to calculate this from the negative infinity to up to b, and then plug in the probability density function here. And then you may also be interested in the region where what is the height of a tree that are in between a and b. So these are like less greater than. So x greater than a and less than b. Then in this case, you have both upper bound and lower bound. Then to get the probability or p of that, so if you want in discrete case the p or the probability of this event, then you will have a to be the probability density function dx. Okay, so this is the one extra step that when you are given a way to, when you are given a probability density function to measure or to describe a random behaviors that are no longer discrete, they are continuous, you can use the density function to calculate the probability. And the idea is through the integral. Then with upper bound a and b. Okay. And also one more comment is that for the continuous case, we don't say something like, what is the probability of x exactly equal to a? What is the probability that the height of a tree is exactly 7.15 meter or 9.52 meter? The probability that is exactly that in a mathematical sense is always equal to 0. This is like if you're evaluating an integral from a to a dx for a density function, this will always be 0. So when you write things here, it's okay to write like equal than or less greater than and equal than, but that equal sign there will have a mass when you calculating this integral will be equal to 0. So it will contribute. So in broadly speaking, it will contribute nothing to the quantities or the probability or that integral that you're calculating. So we will never say for the continuous case, what is that random, let's say the height of tree equal to exactly 7.15, because that when you calculate the integral, it will always give you 0. We are only interested in the range. So in this forest, what is the probability that the tree is greater than 10 meters? What is the probability that the trees in this forest is between 5 meters and 10 meters? So we're interested in calculating, or when we talk about the probabilities, we talking about the probabilities in that sense for the continuous case. So that is one key differences in the between the discrete random variable and the continuous random variable. Yeah, but to calculate the probability, again, you will need to borrow the density function, and if it is for a very complex case, you will need to identify what is that new density, and then calculating the probability through an integral. Okay, so any question or comments up to this point before we go into an example? Let me see if there's any chat. Yes, midterm 2 next week, and I'm going to post homework soon. Yeah, any question or comment up to this point? Okay. Just a quick recap. When we're talking about the probabilities, we need to borrow the probability mass function, density function. For continuous case, we just need to do one more extra step, the integrals. And then you can talk about the probability greater than something, less than something, or in between. You will need to calculate the integral. And the thing here is that you need to manage the upper bound, lower bound for your integrals. And then we don't talk about probability that exactly equal to something, because when you evaluate an integral from a to a, it will always give you 0. It does not contribute mass, or in this case density, in your probability. Okay, let's take a look at one example. Here, let's start with this example. In the last 40 years, there have been 200 earthquakes. Okay. And also as a side note, what is given here is data or info. Okay, so these are the things that you as a researcher or scientist will go out there in the nature to collecting those. So even it's just a simple count. So for example, you need to count for 40 years, you need to get these data. So for lots of things that we're performing analysis, is that you need to require data or information regarding some random systems that are like, for example, in a casino or something in that. Well, that would be yeah. So you need to collecting data to perform some analysis. Okay. So in this context, in these examples, the first sentence here are just the data provided to you, or you need to go out there in the nature to collecting these data and then perform a subsequent analysis. Okay, so here these are all just data. Okay, so once you know that from your collection or from your research, you might want to you might be asked, what is the probability that there will be, okay, exactly 6 earthquakes in the next 2 years. Okay, so now you are given the data. We are interested in particular things. What is the probability that would be exactly 6 earthquakes? So now notice that I'm asking for exactly 6 earthquakes. So here, let me ask, is this question belong to the discrete regime or belong to the continuous regime? Discrete. Yeah, thanks. So right now, this is still in the discrete regime. Yes, thanks. And then to evaluating this, let's start with the discrete regime. And my follow-up question later will be how we I'll ask another question. Then we will see how the continuous case come in, or how we move things to the continuous regime. So now let's start with this context, this background, this examples. And now we notice that this is a discrete regime. And then in the discrete case, we have the binomial Poisson. So here, let me just start with the Poisson case. But you have already seen that you can always navigate or play using different tools that you have to calculate this. But now for this example, I'm going to use the Poisson case. Okay, so now the things, when we choose to use the Poisson, we need to get the lambda here. So the lambda, which is the expected value, the counts that you will get on average, the expected value that you will get. So that is the expected value, that the number in this context, number of earthquake that you will get. Okay, so here we will need to standardize it in a kind of like in a standard scale. So in this particular case, we'll first need to maybe let me not start from here. Let's calculating some okay, so one thing to notice here, I'm also asking for the next 2 years. So we are talking about the things that are in the domain or in the range or in the scale of a year, 1 year. And the data that we are given is that it is the 200 earthquake out of a 40 years time window, time span. So we need to manipulate. So in this real problems, we will need to perform some manipulation to get the rate or the average that are in the same scales that our probability or the things that we really want to calculate. So we need to make sure that the things or the number that are in the same scale in the same in our discussion. So we are given that some information about the 40 years time windows, but we are interested in the probability of in the scales of 2 years. So we need to perform some manipulations so that we are discussing the things here in the same scale. Okay, so first of all, we need to get 200 earthquake divided by the 40 years. So this will give us a number is about 5 earthquake per year. Okay, but again, this is in the scale of 1 year. But the problem, or in the prompt, that we are interested in the scale of 2 years. So we need to do one more thing, is that 5 multiplied by 2, and this will give us 10 earthquake per year. Okay, per 2 years. So when we're talking about some real problems or some in the real world context, then we will need to feed into our model or in our density or our mathematical tools the correct scale, so that we are discussing the same we are discussing the problem on the at the same levels. Otherwise, the measure or the numbers here might give you wrong answers. Okay, and now we know that on average, we were obtaining 10 earthquake in the 2 years. And now back to the expectation of the Poisson, this will give us the lambda. So we are converting the information or the data from the data as some other information that is useful to our probability mass function. And here, the 10 that we get out of 2 years is essentially the average number for our Poisson way of thinking this problem. So our lambda in this case will be equal to 10. And now back to the question is that we are interested in exactly 6 earthquake, and we are interested in x equal to 6. And we are discussing this in the Poisson distribution, so let's bring in the Poisson probability mass function. And then e raised to the power of negative lambda. Lambda here is the 10 here. We raise the power of negative 10, and then 10 raised to the power of the k. Okay, so in this case it's 6. We're interested in 6 earthquake in that 2-year window, and then divided by 6 factorial. Okay, so again, we're still talking about a discrete case. In this real problem with the real context, we need to perform some transformation or manipulations on the information that we collected from the nature into some information that is useful for the probability mass function. We get that 10 is our lambda in this case. We plug in the number, we are able to get the probability. So let me use a calculator. Give me 1 second. This is about 0.063. So to answer our question, then what is the probability that there will be exactly 6 earthquakes in the next 2 years? That will be your answer, your Poisson way to thinking about this problem. Okay, now let me ask a follow-up question. What is the probability that there will be at least 3 months until the next earthquake? Okay, so now this is a new question. I'm asking again the probability. So now we're talking. So of course we're now moving in the regime of we're ready to talk about probabilities. So the question will be always asking for the probability of something happens. But now our subjects here is that what is the time? Is related about the time. So we're talking about will be at least 3 months until the next earthquake here. So now if we draw a time horizon, let's say we're starting at 0. So here we might have 1 month or 1.5 month, and then also 2.15 month until the 3 month. So we are interested in knowing what is the probability that the next earthquake we will have at least 3 months until the next earthquake. So if the earthquake happens on the 3.12 month, then it also satisfying our interest of our interest to knowing that it's at least 3 months until the next one. So the next earthquake can happen in anywhere in after the 3 months. So we are interested, our subject here is the time, and we are interested in anything that is going to start from or after the 3 months. So if we're able to measure or to calculate the probability under this criteria, then we will be able to answer the question of the probability. And we know that the probability in this, okay, let me take one step back. So we are interested in the probability that anything after 3 months away from our current time point. So anything happens after 3 months satisfy that at least 3 months until the next earthquake. So now let me ask a question. It is continuous case or it is a discrete random variable of our subjects of study here?
Continuous.
Yeah, thanks. Yeah, so now we are talking about the continuous case. Because the time here until so at least 3 months until the next earthquake, it can be any of these values, 3.51, they all satisfy that they are at least 3 months away from our current time point that the next earthquake happen. So anything that's happening in this shaded region will satisfy our definition. And then we can see that it can happen in 3.12, 4.51. So all these are continuous time window. So we're now talking about the continuous random variable. Okay, now let's go back to our problem or our prompts here that see the info. We know that the data that we collected here, or the information that we have here, is that we know that we have 40 years, and then there were 200 earthquake. Okay, so and then the question is that we are interested in at least 3 months. One thing to notice immediately is that now we are talking about in the scale of month level. So that also give us a hint of that when for the information that we have, 200 earthquake out of 40 years, that's the information at the year level. So when we work on this problem, we need to convert something into the month level to facilitate our discussion here. Okay, so that is one thing to notice. And now we also notice that this is a continuous case. So now let's think about what are some continuous probability density function that we have we have in our toolkits that are able to calculating this. So the first the simplest one that we have in our toolbox is the exponential distribution. And also, just to give you an idea, we can also use gamma. We can also use normal based on your assumptions, based on what your belief these are all probability density function that can measure continuous case. So they are all your tools to calculating this, but you might run into some other issues. If we have time, we will talk about that. But now let's focus on the simplest one that we have, which is the exponential distribution. Okay, that will handle x in the real case, real values. Okay, let's start from this. And then, of course, just a hint that other continuous distribution also able to give you the same as the answer of the probability of something random. Okay, but now let's work on the exponential case. So here we are interested in the probability of x greater or equal to 3. So again, the equal sign does not make too much, it does not make a difference in the continuous case. Okay, so we're interested in everything, the time. So our subject of our interest here is about time, and then we want that will at least 3 months until the next earthquake. So that is anything that is greater than 3 months is covered or is within our domain of discussion here. So we want x greater than 3. So at least 3 months until the next earthquake. Okay, so anything greater than 3 is that at least 3 months away from our current time point. Okay. And one more thing is that when we calculating in the continuous range, because the probability of everything happening is equal to 1, so we can also consider this is the case that we have the probability of everything happen, but removing from the probability that the things that has happened in between 0 and 3. Okay, so we want to remove the, okay, so if you're able to calculate this, then that is good. You can directly calculate that. Another alternative way is that you can also use 1 for the probability of everything happen, but removing the things that you don't want, which is you're not interested in the probability that will happen within the 3 months. So you can use 1 to remove that. So that will be another option that you can use. Okay, so now because I want to, as a demonstration, I want to use the probability of x less than 3 for using this formula here. So I want to do it that way. But if you can directly do it this way, then you can also evaluate that integral. Yeah, but I want to use the left-hand side as a demonstration. Okay, so my left-hand side is between 0 and 3. So this will cover from, so x less than 3, and then we also have a implicit lower bound that is 0 less than x less than 3. Okay, because we're talking about real context, there will be 0 month. You cannot have like -1 month. So there's an implicit lower bound 0 here. Okay, so I want to use the 0 to 3 as a demonstration to calculating the probability, and then removing that will give me the probability of more than 3 months, or 3 months away from the current time point. Okay, now let's bring in the density function, or the way to calculate the probability. Earlier we said this is the density function, the integral of the density dx. And then we know the thing we are interested is from the x equal to 0 all the way x equal to 3. And then we want to remove it. So this is removed. Then it will give us the probability that is greater than 3. Okay. Now we also going to answer this question in the exponential distribution way. So we will have x equal to 0 all the way to x equal to 3. So that is giving us the region or the case from 0 to 3. Okay, and then lambda e raised to the power of negative lambda x dx. So this is the probability density function of exponential. Again, this is what we choose to use. You can also choose other, but if we have time, we will show that or we'll talk about that later. Okay, but now let's just think that if you believe this is aligns with your intention of analysis, we will use exponential. Okay, now to calculate this probability, we need to evaluate this integral. Now, let's start from this integral here. This will, maybe I will start from here. So the integral of lambda e raised to the power of negative lambda dx. Let's see. Okay, so first of all, there's only one x, so you don't need anything like integration by parts. And for this one, you can immediately applying like formula things to, so this will be, it's more like a formula, like e of negative lambda x. So this is just like a in your calculus class that the antiderivative. And if you want to verify this, is that you can take the derivative again with respect to x, and then negative e negative lambda x. Okay, so if you take the derivative of that, you will have the negative value first. E raised to the power of anything when you take derivative is e raised to the power itself. Now you also need to apply the chain rule to the power, then you will have another copy of negative lambda. And then this will give you a positive lambda in the front, e raised to the power of negative lambda x. So this is for verification, verifying. Okay, so this is saying this is the antiderivative. This is the integral of this thing here. So negative e raised to the power of negative lambda x, or negative lambda x, when you take the derivative, you will get what you have on the left-hand side. And this is the right-hand side. Okay, so, and then we also verify that this formula is correct. So you can always verify your integral by taking the derivative from the right-hand side, and then if you are able to get the right-hand side. So take the derivative of the right-hand side. If you can get the left-hand side, then your integral is correct. Okay. So continue on our equation. 1 minus our integral. So the integral that we get is negative lambda, exponential negative lambda x. We also need to evaluate this from x equal to 0, x equal to 3. Okay, let me pause here to see if there's any question up to this point. So for calculation of the probability in the continuous random variable, it's all about integral. Any question up to this point? Hey, let's continue. 1 minus. So now let's bring in x into the picture. We have negative e negative lambda. Let me put 3 lambda here. Plug in x equal to 3 lambda, minus a negative e raised to the power of negative lambda multiplied by 0. Okay, so anything raised to the power of 0 will be equal to 1. And then this is saying 1 minus 3 lambda minus a minus of 1. So it's plus 1 for the second term here. When you further simplify that, you will have 1 plus e. So now I'm just removing the square bracket. Negative 3 lambda. You have a minus in front of the plus 1, so it's a minus 1. That is the e raised to the power of negative 3 lambda. So that is the probability of the greater than 3. But we have calculating the integral from the x less than 3, and then the range is from 0 to negative 3. And then we'll get this final formulation. But now the problem to get the final problem, the actual numbers, you will see that it involving a lambda here. So the key question is, what is lambda value? What is the value of the lambda here? Then if you have the lambda, plug in, you will able to get the formula, the number here. Back to our question. We know that we have 40 years and 200 earthquake. Also, okay, so now let's revisit our information here. We have 200 earthquake out of 40 years. That is 5 earthquake per year. Okay, but this is in the range, this is in the year level. We are also interested, our question here is in the month level. So we'll also need to divide 5 by 12 months. So that is the number of earthquake per month. And now this will give us the lambda. Let's bring it to the final calculation. The probability that x is greater, that is at least 3 months away, we will get the next earthquake is the e raised to the power of negative 3 multiplied by 5 over 12. This will give us, let me use the calculator here, negative 5 over 4, 0.28. Okay. 0.2865. Okay, so for our follow-up question, we notice that things are continuous. This one, the earthquake can happen anything after 3 months away from now, and then we can choose the exponential distribution to facilitate our calculation of this probability. Then we choose the probability density function here, PDF, of the exponential here. So this is the definition of the probability. Up to here, up to your choice. How you want to analyzing this real event. Okay, so similarly like in the previous case, you can choose binomial or Poisson in your discrete case analysis. Here you can also choose exponential, let's say gamma, and normal. Okay, so up to your choice based on your analysis here. And then the rest, mathematical calculation again. So mathematical is your tools, operations are your tools to facilitating your final calculation. Here is the real context, so you need to real info from your data that you collected. So you need to slightly manipulating in your context, like for example, taking care of the years to the month conversion. Finally, you, here, just use calculators to calculate those. Okay, so yeah, and I think this give you um, a demonstration of how to calculating probability of something under the continuous regime. And then it's all based on the density function and also some mathematical operation like integral to calculating this. And then for your context, when you're handling patient data or some real data, then you need to manipulating some of your information. Okay, so let me stop here and thank you very much.
Thank you.